Hi guys, this is Marco with Students Teach Orgo. Today we are going to go over secondary and tertiary amine synthesis. This will likely be a shorter video, so let's just jump into it. One of the first ways of making secondary and tertiary amines is by using amides. Now we know that we can react an acyl chloride with an amine. In our case, we're going to do a primary amine. And then that will create this amide here, where the nitrogen bridges to this ketone and also the R group that it initially had. And then we can react this with some sort of reducing agent, typically lithium aluminum hydride, just because this is one of the stronger ones. And then that will get rid of this ketone oxygen here, or the amide oxygen, and then that will leave us with a secondary amine. Now the same process also works if we have an acyl chloride and react it with a secondary amine, and then that will give us a tertiary amide instead, tertiary amine instead. Another method that we use is reductive amination. This involves using either an aldehyde or a ketone and some kind of amine, and when both of these are present in aqueous acid, what we end up generating is this iminium ion here, where the amine nitrogen kind of replaces the carbonyl oxygen from the aldehyde or ketone initially, and here we have the this gives us a formal charge on the nitrogen, and this actually exists in equilibrium in solution. If we remove one of the hydrogens on either of these alpha carbons here, what we end up generating is an amine instead, or an amine, where the nitrogen loses its formal charge, the double bond reverts to single bond, and then we form a carbon-carbon double bond with the carbon that's bound to the nitrogen and also one of the alpha carbons. This exists at equilibrium in solution, and then if we react that with this sodium cyanoborohydride, this is a reducing agent, this will reduce the aminium ion only and give us our, in this case, tertiary amine. I just want to stress that that this occurs with the aminium ion. There's always an equilibrium between the aminium ion and the enamine, and this sodium cyanoborohydride reducing agent only reduces the aminium ion directly. If we reduce aminium ion in solution, then the existing enamine has to turn back into the aminium ion in order to be reduced to the amine that we're trying to make. And then lastly, this one isn't so much amine synthesis, but I guess kind of an amine degradation of sorts. This is the Hofmann elimination. So if we have some sort of amine that looks like this, we can react it with something like methyl iodide in large excess. And what that will do is that will replace all of the hydrogens on this amine nitrogen with, in this case, methyl groups. This is a process known as exhaustive methylation, and it will add the maximum number of methyl groups to this nitrogen. And in doing that, this nitrogen with the three methyls, so I guess like a trimethyl amine, this becomes a really good leaving group. And so what we can do is we can eliminate one of the hydrogens on the adjacent carbons here, either this one right here or this one right here. That will drop down and form a double bond, a carbon-carbon double bond here, and then subsequently we will kick off this trimethylamine leaving group. This is facilitated by this silver oxide and water and some heat. And what we end up with is two products, but a very large selectivity for the Hofmann product here on the right, where the double bond is between the carbon that was initially bound to the amine nitrogen and the less substituted adjacent carbon. So this is the Hofmann product. This is about 95% favored. And then we also get this Zaitsev product, which the double bond is between the carbon that formerly had the amine attached to it and the more substituted carbon. Excuse me. But this is a lot less preferred, and this one also exhibits stereochemistry, cis-or-trans stereochemistry. So main takeaway here is the exhaustive methylation process or phenomenon, and then the selection of the Hofmann product over the Zaitsev product. Okay, let's get into some practice problems. Determine the major product for this following reaction, and go ahead, pause the video and come back when you're ready. Okay, so looking at this, right, we have an acyl chloride, and then we have this secondary amine here, so we know that this is going to be done by the amide way of making tertiary amines. Really, all that will happen is this amine nitrogen will replace the Cl here. It will kind of take the same position, and after that we react it with this lithium aluminum hydride, and that will reduce this carbonyl here just to a single methylene group. And so what we end up getting is this product, where again the nitrogen takes that chloride, the chlorine's position, and then we get rid of the double bonded O, and then the mechanism, just the intermediate, kind of looks something like this, where we still have the double bonded O, and then we reduce it to get rid of it. All right, problem 2. Okay, looking at this one, we have an aldehyde and a secondary amine, so this should tell you that we are using the iminium ion pathway to make a tertiary amine. Thinking about the mechanism again, this nitrogen will replace or take the position of this carbonyl oxygen here. That will give us our iminium ion, and then treating with the sodium cyanoborohydride reducing agent, that will just get rid of the iminium ion. The nitrogen will lose its formal charge, and then the nitrogen to carbon double bond will become a single bond. And so our product looks like this. Again, the nitrogen takes the place of the O, and then the double bond is reduced. And mechanistically, it kind of looks something like this. So again, first is the acid catalyzed step to make the iminium ion, and then the reduction step. And just again, note that this iminium ion is in equilibrium with its enamine pair, I guess you would say, in solution. Okay, problem 3. All right, thinking about this one, this is a Hofmann elimination, so we know that this consists of 2 steps, right? First is the exhaustive methylation, which you see with the step 1 here, with the methyl iodide in excess, and then second is the elimination step. Now, we will begin by adding 3 methyl groups onto this nitrogen here, so that will give us trimethylamine with a formal charge of +1 on this nitrogen. And then our elimination step, in order to do that, we have to kick off one of the hydrogens on the least substituted carbon adjacent this carbon, the carbon that's bound to the amine group. And so that least substituted carbon is this one right here. So one of the hydrogens on here will come off, and then this carbon will form a double bond with the carbon that has the amine attached to it. And so our product will look like this. And then the mechanism kind of looks something like this, where first we exhaustively methylate, and we get this, and then we can take one of the hydrogens off here, and then drop the electron pair down, and then this comes off. All right, and lastly, problem 4. All right, this one might look a little intimidating at first, so let's break it down really quick. We know that this methylamine is one of the reactants, and looking at our product, we can kind of see the remnants of the methylamine right here, just this part, which means that these other 2 bonds that the nitrogen has, so this bond right here and this bond right here, those have had to be facilitated by some kind of ketone group, right? Thinking about the iminium ion pathway of making amines, the nitrogen takes the place of the carbonyl oxygen, and so that's exactly what it's doing here, right? They tell us, what does it say in the problem? Another reactant via 2 reductive emanations using sodium cyanoborohydride, right? So one of these bonds is formed by the first reductive amination, and then the second one by the second. Now, just looking at this, right, we have this kind of cyclohexane ring right here. And then in these two positions, they're one carbon far apart, so that cyclohexane ring is just going to have two carbonyl groups, one carbon apart. And so our second reactant looks like this. And then just to kind of illustrate this more, to think about this in reverse, right? We have our product up here, and then the first reverse step would be to oxidize it, because going forward we're reducing it with the sodium cyanoborohydride. So to oxidize this, we turn one of these carbon-nitrogen bonds down here into a double bond, and then our nitrogen will get the plus charge again. And this is our aluminium ion, so recall that it exists in equilibrium with the enamine form. And then by deprotonating, in our case, right, going forward would be the protonation in aqueous acid. We can break this bond and then restore the ketone. And then we have this part of the amine still bound to the ring. And then again, to now do this, the second reductive amination in reverse, we do the reverse of the sodium cyanoborohydride reduction, turn this into its aluminium ion. Again, this exists in equilibrium with its enamine. And then finally, we just have to deprotonate, right, the reverse of protonation. And then that will replace the N, or this methylamine here with the ketone oxygen again. And so our two reactants are this methylamine and then this cyclohexane ring with the two carbonyl groups.